So let us recall what we've been doing last time. The question was, how can we quantitatively estimate the importance of fluctuations which are systematically neglected in the mean-field approximation? Under what conditions the mean-field approximation works well? And can we indicate the range of basic parameters of the model when the mean field works, as well as the other range when it no longer works at all, or maybe with some limited degree of validity. So to this end, what we did, we wrote down the free energy, the expansion, free energy expansion in the spirit of Landau, or Ginzburg-Landau, better to say. We switched on, of course, the gradient term, which is important, because that's exactly the measure of fluctuations, right? If we don't have a gradient term, we have only uniform configurations, and the other parameter doesn't fluctuate from point to point, so there's nothing to discuss there. Then we said the following thing, that if we are able, when we first define the action as the free energy in units of the temperature, we call it the Euclidean action. If we are able to represent it in the form some parameter gamma times, again, the same action, but the action which has the same functional structure. The same functional structure, DDR, with all the parameters, let me put prime here if you wish, with all the parameters dimensionless. That's important. There is no parameter in this section which has a non-trivial dimension. All of them just are one, just numbers. So here you have it's 1/2 gradient, the dimensionless field, gradient squared plus 1/2 this field square, and 1/4 e⁴, and nothing else. So you see there is no other parameters except for numbers, 1/2, 1/4, nothing else. So if the section, now please don't forget that the probability, however you denote it, probability of the distribution eta of x, it's defined in the standard way. Let me put it delta f as a function of eta of x, which is of course the same as minus s function of eta, where s is the action, just the problem. If we can show two things, we assume, first of all, that S1 is positive definite, that's for sure. It's never takes negative terms. This is one thing, because all the terms are positive. Yeah. This is one thing. And since there is no parameter, if this expression, if this integral is convergent, it has to be of the order of 1. Because if not 1, then what? Nothing. Of course. So therefore, if we can show that with S1 being of the order of 1, let me put it like this. I don't know what this number is. I don't care, actually, as a matter of fact. What I do care about is if I can show that gamma, which depends on many on tau and all the other things, the C, which the rigidity, the coefficient alpha, whatever, to C, whatever, if gamma turns out to be much greater than 1, then under this condition I can say that the most probable distribution of the other parameter field, or most probable trajectory if you wish, but most probable realization of this random field is just the one which satisfies the Landau-Ginzburg self-consistency equation, the mean field equation. So this condition ensures that there should exist a range of applicability of mean field for sure. If it is not the case, then of course you are lost if mean field doesn't work at all. At least having this, you can start thinking about it. If you don't have this condition, if gamma turns out to be order 1 or even less than 1, then you are lost. Because fluctuations will be huge. The logic is very simple. If gamma is very, very large, even a small deviation from the classical trajectory, by classical trajectory I mean the one which is derived from the Ginzburg-Landau equation, which is the one which describes the mean field solution of the problem. Any small deviations from that solution will cause huge changes here. They will immediately enlarge the value of S1 because the minimum of S1 corresponds to the classical trajectory, and with gamma very large, it will give you a negligible small probability. This explains to you why only main trajectory survives. And as I said, it is very much in the spirit of the Feynman approach to quantum mechanics. Feynman describes quantum mechanics as a classical mechanics with the only but very important difference. In classical mechanics, we minimize the free energy, we minimize the action and find the trajectory which corresponds to it. And this gives us the Euler-Lagrange equation to find out the trajectories of all the particles. So if you fix the initial point, you fix the final point, and you have only one trajectory which can be derived from the minimal action principle. This is how classical mechanics is formulated. In quantum mechanics, you have the initial point and the final point fixed, but you consider all possible trajectories, not only the one which corresponds, which is described by the Euler-Lagrange equation, all of them. And what happens in this quasi-classical limit, this bunch of trajectories shrinks into a narrow channel, into a narrow tube, whose transverse direction is of the order of Planck's constant. And then you say that in the limit when h goes to 0, this tube shrinks into a line, and this line is just nothing but the Euler-Lagrange curve, the curve which describes the classical trajectory of a particle subject to Euler-Lagrange equations. Very, very much what we have with what we, so very much so in our case, right? Very, very close. All right, so what we were able to show is the following. We were in a hurry, so therefore, yesterday we didn't pay much attention to some details. The conclusion we arrived was as follows. There is some number n. I will remind you what this sort of number is. And this parameter was gamma. And according to our assumption, this product has to be much greater than 1 when n bar and star is the ratio of two volumes. The volume, the interaction volume. The volume which includes within which all the particles interacting with the central one are included. This volume, which has the radius roughly equal to the radius of interactions in the system, bare interactions in the system. We call them R0, right? But there is another one. Okay, no, we call them psi naught. And R naught of D is just the minimal elementary volume, like a unit cell volume. It's a minimal scale which is always present in the problem, and this describes the range of. So this is the central particle, and we have many others. Right? And n measures just this number of these particles within this volume with the radius psi. And if this number is large, then many particles are involved in interaction, and then you expect that on general grounds that mean field should work well. This is what you expect. But in fact, it's not as simple as I said right now. This quantity can be either much larger than 1 in case of long-range interactions, or it can be maybe of the order of 1 for short-range interactions. And so I notice of the same order of so. Imagine that you have, say, 2 or 3 dimensional layers, the number of lattice sides, so the cubic lattice is finite, either 4 or how many? Either 2 or 4. And only nearest neighbors are involved. 2 or 4 is not a big number, therefore n star is of the order 1. To me, 4 is the same as 1. Right, so this has to be distinguished. 2 possibilities. Tau is, of course, small. You are close to GC. So therefore, you have a small parameter. Now, one thing becomes absolutely clear. Case number 1. D is larger than 4. The space dimensionality is greater than 4. Then, this exponent is negative. Tau in this power is a large number. And is either the large number or is of the order of 1, but this is definitely a large number. So this is always satisfied. Everywhere, whatever is tau, however small it is, you may hit the point, the critical point, even there everything works perfectly. So you conclude, in this case, whatever is n star cannot be less than 1. It's of the order of 2, 4, maybe much greater than that, but doesn't matter. It helps the large values of n help satisfy this condition, because the main effort is taken not by this, but by this term. So therefore, in dimensions greater than 4, for any range of interactions, for long-range Ising model, or short-range nearest neighbor Ising model, everything works well. Well, you can perceive it like this, that the Z, the coordination number, which is quite 2D, if Z is greater than 8, because D is greater than 4, mean field works well on a hypercubic lattice. The problem emerges in dimensions D less than 4. If D is less than 4, then this is a small number, multiplied either by a number of the order of 1 or by a large number. Right? Let us start with the case when n star is of the order of 1. Let us consider first a short-range interaction. When the number of particles involved in the interaction is of the order of 1, 2, 4, 6, but not 1 million. So then we have a major problem. If D is less than 4, this is a small quantity. And it has to be, the whole product, it has to be much greater than 1. So you see that for short range, Ising model, mean field does not work at all. At all means there is no vicinity of the critical point, but it might work. It works nowhere. And that's a typical example is just the case of, say, 3-dimensional magnet. The exchange forces in magnetic materials are short-range because these are associated with the overlap of the electron clouds or shells of the D or F electrons. These are deeply located inside the atom, very close to the nuclei. So the overlap is very, very small. So there is no need to consider overlap of a given atom, magnetic atom, even with the neighbor farther than the nearest neighbor, than the nearest one, right? So therefore, the nearest neighbor interaction is a perfect approximation for magnets. So for that case, since the dimension is 3, and n star is of the order 1, mean field simply doesn't work. All these theories, like Curie-wise, whatever, they have only qualitative meaning and qualitative value. Quantitatively, they can only describe sufficiently far regions from the transition point just to tell you there is a paramagnetic phase, there is a ferromagnetic phase, there is a transition. Everything is described correctly. But the vicinity of the point, critical point, is not described correctly because it completely underestimates fluctuations. And now in the second situation, what happens for long-range interaction, Ising model? For a long-range Ising model, there is a competition. This parameter is small, d is less than 4, this parameter is small, but this parameter is large. So you multiply a large number by a small number. The result may be any. It depends on who wins what. So you write down then, rewrite this equation in the following form. Tau to the power of 4 minus d divided by 2 should be much greater than 1 over n star. Now this is a small number. Or otherwise saying, tau should be much greater than some number gi, it's called the Gilbert parameter, which is nothing but 1 over n star to the power of 2 minus, I'm sorry, it should be the other way around, right? So I have to overturn it. 2 divided by 4 minus 2. You can substitute this if you wish. So this parameter is much less than 1. And therefore, if this condition is satisfied, I intentionally write down plus gi and minus gi, just to show that there is a finite range. This is the, and 1 is somewhere very far. So t and 1 is, okay. So I assume that everywhere here, tau is much less than 1. So outside this region, as long as tau is small, much smaller than 1, but on the other hand, much greater than gi, everything's fine. There is an interval. There is a vicinity of the phase transition point, but not the immediate vicinity, not the very close vicinity, far away. You are close, but not too close. Then the mean field works. But if you penetrate deeper, if you overcome, cross this point and occur inside this interval, which is the case right now. It's much less than the Gilbert parameter. You say bye-bye to mean field and have to look for something else. And the result will depend whether how lucky you are. Now, concerning the examples, and one example I already gave you, that's the case of magnet, but there is a counter example when the mean field works perfectly well. This is this case when d is much greater than, d is less than for a 3-dimensional superconductor, in which the correlation length, psi naught, far away from the transition estimate is of the order of 10 to minus 4, 10 to minus 5 centimeters. What is that physically? The physical meaning is this is the linear size of a Cooper pair. In superconductors, Cooper pairs are created. Pairs of electrons with opposite momenta and opposite spin projections form bound states, transform into bosons, and these bosons as Cooper pairs as bosons condense. Just go to a condensate with the same total momentum equal to 0. That's the ground state of a superconductor. But the scale is large as compared to R0, which is 10 to the minus 8 centimeters. This is the 1 angstrom. This is the typical wavelength, if you wish, of the electron close to the Fermi surface, or is the average value between the electrons or atoms in a solid. It's 10 to minus 8. And the ratio of this by that gives you 10 to the third, 10 to the fourth power. Right? Psi naught by R naught. It already gives you 10 to the third. And if you take the third power, then you get something like this. That would be the ratio of the volumes. So you see, the number is huge. Huge. That means that you can forget anything about fluctuations as when you think about the transition, the superconducting transition from a metal state with condensed Cooper pairs. This is why after the discovery of, well, it was a discovery in a sense. Discovery of the microscopic, consistent microscopic theory by Bardeen, Cooper, and Schiffer. Everything was understood within several years. There was a boom, an explosion in literature. Everything was done just in 2-3 years. Yeah, so there are examples and counterexamples. So at least we understand now that d equal to 4, d equal to 4 is the upper critical dimension, static for which and above, at d equal to 4 and above, the midfield theory is correct. It's simply correct. If d is less than 4, then many things depend on what kind of interactions you have. Short range or long range. For long range interactions, you have a chance. There is a window. But for short range, nothing else. Any questions here? Because we are basically there. All right. So we are passing now to a related question, but which sounds a little bit differently. We simply start realizing that the stronger fluctuations are, the smaller is Tc, the critical temperature. Why? Because the fluctuations have a tendency to destroy long-range order. Phase transition is a result of competition between energy and entropy. Now, entropy is related to a disorder. Fluctuations are very sensitive with respect to the number of particles involved in the interaction body. So if this number is not large, is not particularly large, I would say, then the effect of the internal molecular field in the mean-field period will be much less pronounced than it would be if the number of particles in the interaction was large. Because large numbers mean small fluctuations. Small numbers mean large fluctuations. Right? Big societies, even at the level of sociology and politics, however good or bad the regimes may be, are more stable because fluctuations are smaller. Small societies, however good the regime is, are more vulnerable, more dependent on outer conditions and things like that. That's a kind of speculation, of course, not serious. Maybe serious, maybe not. I'm not an expert. The lower critical dimension, therefore, is a dimension when you lose long-range order at any finite temperature. The lower critical dimension is a dimension of a system which in higher dimensions would display a perfect long-range order below a certain finite temperature Tc, whereas at this dimension and below it, it shows nothing. It displays only a disordered phase. Okay, but T equal to 0, at 0 temperature, just proceeding from the fact there is no contribution to the entropy, right? Only energy remains, and all energy always wins when there is nothing to compete with. So therefore, that at 0 energy, whether the system is classical or quantum, well, okay, quantum one has to be accurate. Because in quantum case, fluctuations may exist even at 0 temperature, the so-called 0-point motion. Let's stick to classical picture. In classical models, the result essentially depends on the symmetry, it turns out. In systems like an Ising model, the lower critical dimension is 1. That means that in all dimensions greater than 1, the Ising model, that you already know very well, right? The Ising model, in all dimensions greater than 1, displays a phase transition. The most famous, perhaps, is the Onsager solution of the two-dimensional Ising model, defined on the square lattice. That was the first manifestation when mathematically rigorously was shown that such transition does exist. That was done in ancient times, we can say now. An extremely important contribution to statistical physics. It's very hard to compare anything, perhaps Boltzmann's or Gibbs's contribution, early contributions can beat it. It's not the right word, the right term to use it. There is no competition, so the physics is not about sports. It's not about who is better, Rafael Nadal or Roger Federer. So it's not about that. I stand for Federer, but many other people prefer Nadal. So it's all right. So, for systems with discrete symmetries, like Z2, for instance, Ising. The lower critical dimension is 1. And this is basically what is called Landau Peierls theorem. No phase transitions in one-dimensional systems with a discrete symmetry group and short-range interactions. That's important. Short-range interactions. I have to add here plus short-range interactions. Now, if you have a continuous symmetry, for instance, O2 or O3 or ON, for instance, then the lower critical dimension is 2. I would say that perhaps it goes under the name of Mermin-Plagler theorem. So these are two theorems of fundamental importance in statistical physics, in particular in the theory of phase transitions. It's impossible to say that I think I know something about phase transition if you don't know either of these two things. It's absolutely compulsory. So let's start with the first case and consider the one-dimensionalizing model with nearest neighbor interaction. You can assume that you apply the periodic boundary conditions like this. In other words, you fold your system into a circle, into a ring. So this is 1, 2, 3. This is n minus 1, and this is 1, which is the same as, okay, I'm sorry. This is n minus 1, this is n, and this is 1, which is the same as n plus 1 before. Just periodic boundary conditions because perhaps it's one of the most convenient way to do all the necessary bookkeeping. J is positive. J is positive. If the temperature is 0, there is no entropy in the business. So we have to know what is the ground state. What is the minimal energy state? And we know already there are two such states. It's a combination of, all the spins polarized upwards, or as well as the other state when all the spins are polarized downwards. And this follows just from the Z2 symmetry of this model. Every configuration, every spin configuration has its counterpart, which is obtained from the original one by overturning all the spins simultaneously. So therefore, if we say this is a ground state, this has to be another one because of the Z2 symmetry. And then we say the ground state is degenerate. The ground state, any of these two ground states break the original Z2. Z2 is the symmetry of the Hamiltonian, or the free energy, if you wish. The minimal energy state does break this Z2, and under this action, Z2, this transforms to that, this transforms to that. So none of these is the negative under Z2. Z2 is spontaneously gone. This is what happens at t equal to 0. This is for sure, because again, you don't need to invoke anything but the energy considerations. Energy takes its minimal value just for these two configurations. And there is no entropy to compete with. Now let us switch a small t. Let us assume that t is much smaller than j, because j is the measure of energy according to our model. The typical gap is of the order of j. So let the temperature be much, much, much smaller than this gap. At the gap from the ground state to the first excited state. How can you build an excited state in this case, right? So you start with, suppose you start with this ground state, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even. So what you can do the following thing. You can overturn, for instance, this spin. Consider this configuration. Now suppose you know the ground state energy E naught, which can be easily calculated. I don't want to do it anyway, I just can write it down immediately, but why should I? I know that when I overturn one spin, I break two bonds in a sense. So therefore, the excitation energy, the energy minus of this configuration minus the ground state energy, let me call it epsilon. Okay. Let me do the following thing. If I had a configuration up, and I had turned it into a configuration up, down, the energy change epsilon naught would be 2j. Do you agree with me? Not J, but 2J. Right? But now I have two nearest neighbors. So therefore I should write down, and I will call it epsilon naught twice epsilon naught. In this case it gives me 4. But now the question is, what will happen if instead of this I had considered such configurations? Same number of spins, same 10 spins. What is the energy of this configuration in your opinion? What is the excitation energy for this kind of configuration? Who can come up with an idea? What is the difference between this and that?
No difference.
Huh?
No difference.
No difference.
Yeah.
Why?
Because the thing that matters is up, down, like just at the board there, and
Why not this?
because they are parallel, so it's G2 symmetry. Like if
No, why not this to that? Why you don't care? Why you don't care about the coupling between this and that?
aren't we taking this first nearest neighbor?
Yes.
Okay.
So that's the point. That's the crucial point. The most crucial point is that there is no interaction other than between nearest neighbors. This is why, if I consider this piece, so if this is the part of A phase, here I have an inclusion of B phase, right? So this is A, and this is B. The B phase is degenerate with A phase, so therefore, if I didn't have these things, this configuration, 1, 2, 3, 4, 5, 6, 7, up, 3, down, will have the same configuration as all of them up. The only difference comes from the, what we call, the domain walls. Because I have 3 domains, the A domain, and inclusion of a B domain. And there is a border between them. This border is called the domain wall. When the magnetization goes from this to this, so if I measure magnetization, here I measure sigma, here I measure the distance at some x equal to x naught. I have a domain wall when the magnetization rapidly changes from up to down. Sometimes it's called kink. Domain wall or kink. These are synonyms. You may use either. So now it turns out that I have 2 kinks, and the energy per kink is just epsilon. So this configuration, I can enlarge the B domain and a little bit make shorter the A domain, as long as I have the configuration of type ABA with 2 domain walls, the energy will be just the same. So the huge degeneracy you can see. The location of your kinks don't matter much. The number matters. The location doesn't. Right? So in other words, I can now consider other configurations which can be generated from the ones already shown. For instance, A, B, A, B, A, B. I have to end with A because of the periodic grounded boundary conditions. If I start with A, since I bend my system into a circle, A must transform to B. In other words, the number of domain walls must be even always. If there is a domain wall, this should be an anti-domain wall. There is a kink, it should be an anti-kink as well, right? From plus to minus as well as from minus to 1, to recover from A to A. So here I have, you see, as many boundaries, many domain walls. And every time I look at that, I add the energy epsilon naught to the overall energy of the system. These are how excitations look like. But every time I have this kind of business, A, B, A, B, A, B, this does not support order. These configurations have a tendency to kill long-range order because the average magnetization has a tendency to be much smaller than it would be if all the spins were aligned in parallel fashion. So in other words, excitations support disorder. Now, can the order sustain these excitations? To what extent? So what you need to do, you need to look at the given excitation and build up the corresponding increase or decrease, change, better to say, of the free energy. Why free energy? Because you want to use temperature as an independent thermodynamic parameter. This is why you cannot use simply energy. You need to deal with free energy because you cannot possibly measure entropy in the lab, but you can measure temperature in the lab. Right. So the lowest order excitation is just this one. Well, maybe even this one doesn't matter because the energy is just the same, it's hugely generous. It is clear that if this condition is satisfied, the number or the concentration of kinks will be low. Why? Because if you know that the energy of a single kink is epsilon naught, you build up this exponent and you call this is a probability of having one kink and if temperature is much smaller than J, this is a very small number. If the probability of having a kink is small, so is the concentration of the kinks. Because the concentration reflects the probability of having a given particle, right? That we know. What is concentration? It's psi modulus square equal quantum mechanics. Psi modulus square gives you concentration. Because the integral is 1. All right. So, because of that, I can consider a macroscopic region in which I have two phases, A, two ground state phases, and B, with the boundary between them representing a kink. And let the length of the segment be M. So, in fact, I have something like here, like this. But I take, suppose this piece, this part of the game, I consider only one. Only I know for sure the number of kinks is very small. So therefore, the domains are sufficiently wide. So therefore, I'm entitled to consider a macroscopically large segment of the chain in which two phases coexist, two domains coexist. And then I ask myself, what is the free energy associated with the creation of this kink? What do? I do the standard thing, which is repeatedly done in many circumstances. You simply write down delta F is the excitation energy. The energy is just the excitation energy of a single kink. Is epsilon naught. Minus T times what? The entropy. And the entropy is the logarithm of the statistical weight, gamma. What is the statistical weight? The statistical weight in this case tells me what is the degeneracy in this picture. The degeneracy, which I can see here immediately, is the location of this kink. It can be located here, can be located here, can be located here. I can put the location, I can choose the location anywhere on the same. So therefore, instead of this gamma, I write down this m. So all in all, it's 2j minus t L m. Right? logarithm of n. Because n here is just the statistical weight.
We still have periodic boundary condition of it.
No, no. Periodic boundary condition is taken care of by this construction. Here you are perfectly right. But I'm entitled, since I know that the concentration of the kinks is very small, I can choose any segment, any pair of nearby domains. These will represent macroscopic objects. So I'm asking myself, given one face here and the other, it's a part of the whole system. I'm not asking what happens with the if I prove something which will eventually look bad, if I prove that the system is not stable against excitations. And the simple example, of course it will fail even when I take into account many. Because the more excitations I have, the worse will be the result. The effect of fluctuation will be only enhanced, not diminished. So I consider the best possible case for the long-range order to survive. Only a single kink. If it doesn't survive for a single kink, it will not survive for two of them, for three of them, and so forth. Is it clear? Right? Of course, it should be clear that I can always find such a large value of m at any non-zero t. So this quantity will be less than 0. Because the temperature appears only here, and you can always choose m, the length of the segment, to be large enough to enforce this whole expression to be negative. Negative means that the state I started from is unstable. It's not thermodynamically stable. The state I started from was a full alignment of the spins. And that means that such system, if I switch on a finite temperature, immediately generates a finite concentration of the kinks. In other words, my uniformly polarized segment when split into domains with opposite orientations of magnetization, plus, minus, plus, minus, plus, minus, and on average you will get nothing. Which means that there is no long-range order in the one-dimensionalizing model at any finite temperature, under the condition that, in this case, the interaction goes to nearest neighbors only. In general case, you can say for any finite range interaction, can be nearest neighbors plus next to nearest neighbors, but not too far. So this is the Landau-Peierls theorem, which tells you that this doesn't happen in one. Now there is an immediate example, an immediate question which arises in this case. What if we try to repeat this philosophy for the two-dimensional? We know for sure that since outsider had solved this problem, this argument should not apply to two-dimensional model. It should be wrong. It should have some catches inside. Let's see how it comes about. Any questions here? By the way, you can find this derivation almost in any textbook. It's a canonical thing. We will solve this problem exactly. We will solve the one-dimensionalizing model later on by the end of our lecture course. It's one of the exactly solvable models. It's an interesting model to solve. The solution is interesting. Now I'm bringing only qualitative arguments just to show that there is no phase transition. The phase transition point is t equal to 0. At any finite t, you have a finite correlation rate. Can you come up with the idea? So my claim is that at t equal to 0, you have a long-range order. At any t non-zero, you have full disorder, and that actually means that your correlation length at any finite t is finite, it's less than infinity. Who can come up with the idea what the kind of function it should be, what kind of function of temperature it might be. What is the temperature dependence of the correlation in this case?
It's definitely inversely proportional because higher.
Inversely proportional to what?
Temperature.
Oh, why? So you suggest it's a power law.
Or
Why power law?
like higher the temperature, higher is the fluctuation. No.
That's not a serious argument. General expectation is right, but the argument is not strong enough.
Correlation length is higher at lower temperatures, so
The correlation length increases on decreasing the temperature. You're perfectly right. But how to estimate it? I'm not talking about calculations. I'm not talking about how to calculate. When you have a full solution, you will find out the correlation length. I'm just talking about common sense. So you are a physicist and you want to speculate. What kind of arguments should you involve to figure out the behavior of the correlation length?
Maybe from from delta F, because lower the temperature, we need to increase M for that to be negative. The free energy.
You mean this one?
Yes.
So how would you extract the length?
For example, we know that temperature is always very less than J, that we have taken. So for the second term to dominate over the first term, the log M term should be higher for lower temperature.
Yes.
And this is the log, let's say, we are given a certain temperature, and then we want this to be negative. Obviously, we'll take bigger M.
Okay, so what you're saying is the following, that this cannot be satisfied at any m. It can only be satisfied when m is larger than something.
Something for a given temperature.
And m is larger, in this case m is larger, should be larger than exponent 2j divided by t. It's a huge number, by the way, right? M is what? The length of your segment. As long as m, let me call it m star. As long as m is less than m star, delta f is positive, and everything's fine. How would you comment on that? Let's continue your idea. Let's develop your idea. So your claim is there should exist a critical value of m at which delta f changes its sign. I said I can always find such a large value of m that delta f is negative. But I didn't say, as your colleague says, that there should exist a smaller values of m less than this number, for which delta f is still positive. Which means that for such finite size segments, long range order is fine. But when we say finite size segments and long range order, if you translate it into physically sensible sentence, it will be, we should call it short range order. Because for a larger m, long range order disappears. So the order exists only as long as m is less than m star. At larger m, the order disappears. So what is the correlation like that? You haven't said already everything, so you're left with the half step to make. Your right hand is already in the air. You have to make a step. What is the correlation length? The correlation length is the length when information about a fixed orientation of a given spin spreads away from this point after a certain limit when this information disappears. The linear size of this region is just the correlation. So therefore, if you know that for m less than m star, delta f is positive, and the aligned spins can survive as a stable configuration, but not for m larger than that number, the length of this m star is nothing but the ratio of the correlation length divided by the lattice constant. It's number of lattice sites at which the information spreads. This is the dimensionless correlation length, or the correlation length measured in units of the minimal distance. And you come up with the conclusion that that's exactly the behavior of your correlation length. It's a huge number. When J is much greater than T, then temperature is small. It is exponentially small. It's exponentially large. It's exponentially large because you have a gap in the system. The gap tells you that every time you create a kink, you have to pay energy, 2J. And that's the energy of your kink. So the energy with a minus sign would be the probability. So you could solve this problem just one more logic, very similar to what you have proposed. The logic goes just from here. According to the Gibbs hypothesis, if I have an energy of excitation, which is absolute, the kink is an excitation. So its energy is absolute, not 2J. And the probability of having a kink is this one. Right? Now, the larger is the probability, the larger is the densities, the density of the kinks. Let me introduce the density of the kinks, Nk, which is the number of kinks divided by length, which has to be proportional again to this exponent. Now the question is, what is the length divided by Nk? Is the average distance between the kinks. If you have a density, which is the number divided by length, the inverse density is the average distance between the particles. Correct?
Yeah.
Now, if you have a system which has a tendency towards ordering, and there are some correlations which develop, the correlations are killed by the kinks. So therefore, any length associated with the kinks has to be identified as the correlation length. So therefore, I can simply make a statement that the average distance between the kinks, L between the kinks, is the same as psi divided by E. And then I have this result again. Right. So there are many, many ways of coming to the same result using very quite general but solid, justified arguments. And you have to get used to that. Because physics, especially theoretical physics, is not only about calculating things. That's important. It's about foreseeing the results. You have to develop intuition. All right, so this is what I wanted to say about one-dimensional Ising model. Now let's turn to two-dimensional. Now this derivation is due to Rudolf Peierls, a famous physicist of the 20th century. So we consider now a two-dimensional Ising model. That means the Ising model which is defined on a square lattice. Each lattice side associated with the Ising variable sigma. And there is a standard interaction between the spins minus J and M, sigma N, sigma M, when N and M are nearest neighbors on the square lattice. Not on the line, but on the square lattice. Right. What is the ground state? It's again doubly degenerate. All the spins up, I will notice, label the spins up by pluses, as well as all the spins down, all the spins down. Right? Right. And the energies are the same of these two configurations. These are the ground state energies. So the minimum energies states. How to build up excitation? Of course, the same logic as before. We can insert. If you call this a phase A, and you call this phase B, you may take a phase A and put an island of the phase B inside. Right? If you do that, you will find out that the boundary will represent a closed line. It's no longer a point. So in the one-dimensional case, the domain wall is a point. Here it is a line. Let us try to do it more or less accurately. I'm not sure I will succeed in all this. But at least I will try. I'll change the color. So you see, where is the domain wall? This is the domain wall. Okay? Is it correct?
There is a plus sign.
Now it is correct. So your logic goes exactly in the same way. So the first thing you have to appreciate is again the elementary energy. The elementary energy comes to discussing what is the cost of having opposite spins along a domain wall. This pair, or this pair, or this pair. Every time it costs epsilon naught, which is 2J. Why? Because it has to do with overturning only one spin, and that costs you twice J, right? So therefore, the free energy, the change of the free energy is the energy associated with the domain wall as an excitation. Therefore, it should be twice J times the L, let me call it L tilde. And L tilde is the perimeter of this domain wall, the length. Minus T, and here we have log of some gamma, which needs to be understood. And this is the
Circumference.
don't hurry. It's a more tricky thing. Mr. Peierls was almost a genius. So the logic is as follows: how can you estimate the degeneracy? So you take a square lattice. It's an amazing derivation because it shows you how smart people think. And you take a point which belongs to the domain wall, to the boundary. And then you pose the following question. Imagine that on this square lattice, I have a random walker. I have a particle, or a human being, or some alien coming from Mars or Jupiter, I don't know, who does the following. In units of time, it makes completely randomly steps, upwards, downwards, to the right or to the left. 4 possibilities. In other words, it can go to one of the 4 existing nearest neighbor sites. Right? Okay, fine. Very good. But if I start insisting, and then, for instance, I can count from here to here. Suppose I chose this nearest neighbor site. Now, I'm asking now the same question about the second step of this random walker. Where should it go? Can it go upwards, to the left, to the right? That's fine. Can it go downwards? The answer is no, it can't. Because This is not a random walk on the lattice. This is the way to recover this boundary using this fictitious random walk. So you introduce, you forbid one thing. Instead of 4 possibilities, you leave only 3. No way back. He has to have a memory from where he came. Right? If he occurs here, it has to remember he came from here. So there is no way of coming back. Otherwise, because the boundary is a sequence of elementary steps. Every step should be passed only one. Should be done only once. Right. So Q, therefore, so Q is the number of possibilities. It's no longer 4. It has a chance to be 3. But can the 3 be the right number? If 3 is the right number, the particle coming, suppose, from below cannot go down. It can go to the left, to the right, or upwards, but if there are no other restrictions, the particle will go to infinity in the end of the day, with a kind of diffusion, with a refuse to one step, no way back. The particle will go to infinity, and there is no chance to close the contour. The contour should be closed, don't forget. So there should be other correlation, therefore. The particle should remember actually not only the previous step, it should remember the whole history. If it occurs somewhere here, it should know that the curve must be closed somewhere. So therefore Q must be less than 3. Right? So, let me put M tilde when M tilde is the same as L tilde, but in units of lattice spacing. In other words, I can insist on saying that gamma should be Q to the power of N tilde, and therefore delta F will transform to 2Jn tilde minus T N tilde log of Q. I will push this N tilde outside. I will be left with 2J minus T and log of Q. And there is no big number competing with 2J inside this bracket. It's quite clear that the free energy as an extensive quantity should be proportional to the length of the contour. There is another expression which very well may be positive or negative as opposed to the previous case. Right? So I immediately see that there is a critical temperature Tc, which is defined as 2J divided by the log of Q, such that at T less than Tc, T less than Tc, when this term is less than this one, delta F is positive, and the original system, original state is stable, therefore. Positive free energy excess means that whatever is the excitation, it has a higher energy than the ground state energy. And that's a signature of stability. At T less than Tc, you have a long-range order which is stable against creating of these nasty domain balls. But if the temperature is greater than Tc, then this term wins. It is the leading one. Delta F becomes negative, and long-range order state breaks. So you do have a phase transition. You see? The whole difference between this expression and the one which you had in the one-dimensional case, please notice, the large extensive number M entered the expression of the energy per kink. Nothing like this happens here. M goes out. And here I have just an interplay of parameters. Do you know the exact value of Tc? the exact value of Tc, which comes out from the solution by Onsager, is log square root of 2 plus 1. So this is Q, square root of 2 plus 1. It is located between 3 and 2. That's very much close to what Mr. Peierls had anticipated, even though he didn't have at his disposal an exact solution of the problem, but he figured out that this number Q must be somewhere here. And that's exactly is confirmed by the exact solution. Very nice. This is one of the brilliance of, manifest brilliance of theoretical physics. So, according to Peierls, and this is always called Peierls argument, in two-dimensionalizing model there is a transition. The domain walls exist, they represent accentuations, they tend to disorder the system, but they cannot disorder immediately at arbitrary, introduce disorder and disorder the ordered ground state at arbitrarily small magnetic fields. I'm sorry, about the small temperatures. The temperature should be raised until to some critical level. Yeah.
That it should be smaller than 3.
Smaller than 3, yes, yes.
What is our argument that it should be greater than 2?
Well, greater than 2, well, it's because if you start from some point, you can easily close the contour when moving to the right or moving to the left. And that gives you. If you start from the point, take any point at the lattice. It may be some intermediate point if you're random walk, effective picture. You never know where you close the contour when moving to the right, or moving upwards, or moving downwards, or moving to the left. Right? So you can imagine some arbitrary axis. So this restriction comes from that. It must be less than 3 for sure, because if there is 3, then you go to infinity, you never close the contour. But it should be greater than 2, because if it is smaller than 2, I presume that it will be a completely different universality class. I don't know. Maybe such models exist, but I don't know. So your question may be quite to the point. I know for sure that this follows from the fact from the arbitrariness in the choice of the polarization, if you wish, or direction, in which direction I should close the contour, roughly. But I may be not quite correct. Yeah. At least the exact solution gives me this.
So can't we close the contour by having Q equal to exactly 2? Like a square contour, something like that?
No, Q is equal to 2 it's a bad situation, so which means that if you are on the square lattice, if you are in the square lattice, you are somewhere here. Which 2? Okay, so suppose you came from here, yeah. So you eliminate, so you leave these 3 as a possibility. So which 2 you will, if you insist of saying Q is equal to 2, you break as an isotropy of some point symmetry of the square lattice, I believe. Because which you will choose. For instance, you have chosen this one. You eliminated this one. You don't go to the left. You claim, I don't go to the left. I never go to the left. I never go down, I never go to the left. So therefore I go here and I go here. This actually means that you can only close your contour in this direction. Very much what I said in reply to the question of your colleague. If I choose this one, this will be this one. If I choose the upper one, this will be that one. So, yeah. But maybe some decorated lattices different from the square lattices.
There will be, for example, I was thinking like from this route, let's say I come from this point to this point, then at this point I only take the direction which is perpendicular to where I come from, so go this way. But
No, look, again. Look, all this picture, the picture of the random walk, on the square lattice is a kind of supplementary. It's the way to understand the result. Basically, it goes to combinatorics. You have a clear problem. You have a given number of steps because the length of the contour is fixed. It determined, so therefore you are limited by a fixed number of length. And the other question is, and the other restriction is, the contour must be closed. What remains at your disposal is the topology and geometry of your lattice and the underlying lattice. It's a well-posed mathematical problem. I'm sure it has a solution. I'm sure also Onsager himself knew it. So I don't know in detail because people are inclined to consider decorated lattices, not necessarily square lattices, maybe some, not necessarily triangular lattices, maybe lattices like quadruple lattices. I'm not sure I will be able to draw. I'm not good to draw the lattices. Okay, so, but basically the main arguments are transparent and go quite clear. So this is how it is. Well, in principle, this is it, and there is nothing more left to discuss today, except maybe for one thing, which I will only briefly mention. Life becomes even more interesting when you go to continuous symmetry groups. In other words, when you move from Landau-Peierls arguments and pictures and restrictions and theorems to the Mermin-Wagner. Because the Mermin-Wagner theorem applies to systems with continuous symmetry, and then it tells you that the excitations which exist in systems possessing continuous symmetry are more capable of destroying long-range order than it happens in discrete models, the models with discrete symmetry group. But since we also know that if the symmetry is spontaneously broken, if a continuous symmetry is spontaneously broken, then the lowest energy excitations in such system are the famous Goldstone modes, which recover the broken symmetry, right? So therefore, the limitations which emerge on the dimensionality, we will find out that in continuous symmetry, in the case of continuous symmetries, both one-dimensional and two-dimensional systems always remain disordered. They're never ordered. But the reason, the underlying reason is much more spectacular than here because elementary excitations which destroy long-range order represent gapless modes, gapless. You don't need to spend any energy to excite them. These are like in the Mexican hat potential, you remember? If the potential has this shape, such that there is a finite curvature, if I measure the other parameter, this is the potential energy or the free energy as a function of the other parameter. The other parameter is has the modulus m and cosine phi and sine phi. And then, if I change for a fixed value of the angle, I change the modulus of all the parameter. I have to climb up or go down along this, and the small, close to the minimum, it's a parabola, of course, and the parabolic harmonic potential. So therefore, this motion has to be associated with some vibration, and this vibration energy should be finite, and therefore the finite energy should translate to a finite correlation length, and therefore this is not an interesting thing. This is simply something which keeps m finite. And it should be finite because I'm in the ordered phase. But on the other hand, I can start traveling along this minimum of this narrow channel by changing the angle and keeping m constant. And this is precisely what the Goldstone mode is about. Every time you change the angle, but keep the modulus of this vector fixed, you simply change the orientation of your order parameter. So your order parameter explores the whole circle, the whole space of degeneracy. And any direction is a ground state, any. So therefore, the change from one to another should not be associated with, and should not cost you any energy. Why? Because there is no gap. Because the symmetry is continuous, as follows from here. There is no bumps and no irregularities. It's absolutely degenerate channel. So this becomes important, and the picture of Goldstone comes to the surface. It becomes very important, and the conclusions are quite impressive. We'll find out why in 2 dimensions the long-range order is absent, and then we will discuss a very interesting model, which is the model of planar spins in 2 dimensions, the XY model in 2 dimensions. There is a new class of phase transitions, the so-called topological phase transitions. Some time ago, here at ICTP, we had direct metal presentations by different people, including those who invented all this. And a year later, those 2 people were awarded Nobel Prize, no more, no less. So it's a thing of fundamental importance. I hope we'll discuss it. But for today, it's everything. So thank you for your attention.